In this video, we see Max and Fumie continue their discussion of some of the interesting properties in Pascal's triangle.
Hey Fumie, check out the diagonals in Pascal's triangle.
I noticed that diagonal when you first showed me Pascal's triangle. Those are all the counting numbers. And I thought about it since we talked last, and it makes sense that these numbers are on the diagonal like this. We form those diagonal entries by adding 1 to the term beside it. Like 1 plus 1 equals 2, 1 plus 2 equals 3, 1 plus 3 equals 4, 1 plus 4 equals 5.
Yup, you figured out the first diagonal. Now I'll show you how all the diagonals are kind of related to each other. Ever heard of triangular numbers?
No. Are they like half of squares or something?
Ha! Well, there's no relation to squares, but you can find them in Pascal's triangle. A triangular number counts objects arranged in an equilateral triangle. I'll show you. Tell me, how many dots do you see in each triangle?
The first triangle has 1 dot. The second triangle has 1 plus 2 equals 3 dots. The third triangle has 1 plus 2 plus 3 equals 6 dots. The fourth has 1 plus 2 plus 3 plus 4 equals 10 dots.
You can keep going like this and get an infinite list of these numbers.
These triangular numbers are just the numbers you get from a continued summation of the natural numbers. I can see why this shows up in Pascal's triangle here on the third diagonal of Pascal's triangle. If the second diagonal consists of the counting numbers and the third diagonal consists of the triangular numbers, what do you call the numbers on the fourth diagonal?
Those are called the tetrahedral numbers, which are 1, 4, 10, 20. You get these numbers when you stack gumballs in a tetrahedron or a triangle pyramid like this. So a tetrahedron with a height of 1 needs 1 gumball. If we have a height of 2, then we've used 1 and 3 for the base, so 4 gumballs. For a height of 3 layers, we put the 4 gumball tetrahedron on a base of 6 gumballs to use up 10 gumballs.
I see what is happening. Every time you want to increase the height of the tetrahedron, you are essentially adding a triangular base to the bottom of it. Oh, so you are adding the triangular numbers to get your tetrahedral numbers.
Exactly. Look how you can calculate this sum in the triangle. The next tetrahedral number, the one for a height of 4 layers, is given by the sum of the first 4 triangular numbers. So 1 plus 3 plus 6 plus 10 equals 20.
And for the fifth tetrahedron number, we get 1 plus 3 plus 6 plus 10 plus 15 equals 35. It is really neat how you can start at the 1 in the third diagonal, the diagonal that contains the triangular numbers, and sum the entries and stop at any time. The next entry down diagonally and to the right will equal the tetrahedral number. What are the numbers in the fourth diagonal called? Pentagonal numbers? Pentalope numbers? Pentahedron numbers?
Pentalope, that's funny. Sounds like a mix of an antelope and pentagon. You're so close. Those are the pentatope numbers, and you get those by summing up the tetrahedral numbers.
It looks like you can get entries on one diagonal, but doing that summing thing on the diagonal above it? For instance, look here at the 7th diagonal. You can get its entries by adding up the entries on the 6th diagonal.
Yep, works every time.
It reminds me of socks.
It's actually called the hockey stick identity.
We could call it the hockey stick sock sum or the socky hockey stick sum.